In this video, I'm going to be going over the 3 different types of ladder problems that you might see on the AP tests. So these are dealing with related rates, and they can be applied to any triangles. So the way this video is going to work is that after this, I'm going to be going over the guide as to how you solve these, and then I'm going to be going over the 3 examples. The first one being using 3 side lengths with the Pythagorean Theorem. The second one being finding the area using the base and the height of a triangle. And the third one is going to involve trigonometry, which means using 2 of our side lengths to come up with an angle. So the reason that related rates may be so difficult for high school students is that there's such a wide variety of problems. Triangle problems aren't the only kinds of questions that you'll see on the AP tests. There may be volume problems, surface area problems, problems with different shapes. So the general guide that I'm going to give you will not necessarily apply to all of the problems. There will be some nuances and differences that you'll have to apply. So as long as you go through each problem at least once or twice and become familiar with them, you should be fine to handle them on the AP tests. So let's get into it. So the steps we're going to be taking when solving these problems is we're first going to draw a picture and label all of our values. Our second step is going to be to find a formula using the values that we know. Our third step is going to be to differentiate with respect to time, so differentiate the formula that we found. Then our fourth step is just going to be to plug in the values and solve for the unknown. So let's apply these steps into our first example. I've written them in the top right so it's easier to see. And we're given that a 30-foot long ladder is leaning against a wall. Its base is being pulled away from the wall at a rate of 4 feet per second. When the base of the ladder is 6 feet away from the wall, how fast is the top of the ladder sliding down the wall? So our first step is to draw a picture and label our values. So let's do that. We're given that we have a ladder that's 30 feet long and it's leaning against the wall. So let's just draw that. We'll draw our wall. We'll draw a ground. Then we'll draw our ladder. And it doesn't have to be perfect. We just have to understand what it kind of looks like. So we know that, again, the ladder is 30 feet long. So we'll write a 30 here, 30 feet. And what's important about this ladder is that it is an object, which means that the length of this ladder is never going to change. However we move it, this 30 is always going to stay constant. So from there, we're given that its base is being pulled away from the wall at a rate of 4 feet per second. So let's look at that carefully. We're dealing with the relationship between the base of the ladder, which is this point right here, from the wall, which is this point right here. So the distance we're dealing with is right here, this distance between the wall and the base of the ladder. So what we can do is we can label that distance x. Then we know that the rate at which x is changing is 4 feet per second. The rate at which the bottom of the ladder is being pulled away from the wall is 4 feet per second. So if we write that, that's going to look like dx, which is the change in x with respect to time, is 4 feet per second. So 4 feet per second. And from there, we're asked that when the base of the ladder is 6 feet away from the wall, how fast is the top of the ladder sliding down the wall? So we're dealing with the instant that when the base of the ladder is 6 feet away from the wall, when this distance x is 6. So let's write that here. The instant that x equals 6 feet. How fast is the top of the ladder sliding down the wall? So here we're dealing with the distance from the top of the ladder to the ground, right? So let's just label that y. And if we see here, we're dealing with how fast is it moving. So we know that we're dealing with the rate. So next to this y, let's just write a dy over dt, the change in y with respect to time. So here are all of the values that the problem gives us. Now with the triangle problem, there is one more value that we can pull out of this. Since we know that we're dealing with the instant that x is 6, and we know that this hypotenuse is going to be 30, we have two sides of a triangle which we can use to find this last side. So let's do that. In order to do that, we need to use the Pythagorean theorem. So let's just write that here. A squared plus b squared equals c squared. Then we plug in our values that we know. So if a is x, we're dealing with the instant that x is 6. So 6 squared plus b squared, which is the unknown, so y squared equals c squared, which is 30. So 30 squared. So 6 squared is 36 plus y squared equals 900. Y squared equals 864. And we get that y is equal to root 864. So let's label that. And what this root 864 actually means is the value of the distance between the top of the ladder and the bottom of the ladder when x is 6 feet. Okay? So here we have all of the values that we need in order to find our equation. So if we go up here, we can see that our next step is to find a formula for our drawing. So if we take a look, we know that we have 1 side length, 2 side lengths, and 3 side lengths. So the relationship between 3 side lengths in a triangle can be found using Pythagorean's theorem. So let's write that. Let's see what color it was. It was green. So let's write that in green up here. A squared plus b squared equals c squared. Now this is the equation that we're planning to differentiate. So there we have the equation that we need. And our next step is to differentiate this equation. So let's do that in pink. Actually, first, let's just rewrite this a squared plus b squared equals c squared, so that we're using the variables and values that we have in our drawing. So let's call our a value this side length, so that's going to be x squared plus, let's call b this y, so y squared is going to be equal to c squared. Now, what I said earlier was that this 30 is always going to remain constant. So what I'll do now is I'll just plug it in, since we know that this 30 is never going to change. We may as well just plug it in now. So let's do 30 squared, and that's 900. So something that's important to note is that this a squared plus b squared equals c squared is different than this a squared plus b squared equals c squared. What we're doing here in yellow is we're trying to find the value for what y is when x equals 6. Whereas in this equation, this is the one that we're going to differentiate in order to plug in these dy and dx values. So this one is to find all the known values, and this one is to actually solve the problem. So moving on, let's differentiate in pink. So that'll be 2x, and we're differentiating with respect to time, so it's going to be dx over dt plus 2y dy over dt is going to be equal to 0, because the derivative of any constant is just going to be 0. And here we have our differentiated equation. So our final step is just going to be to plug in the values that we have. So I'll do that in blue. So 2, we know that x is, we're dealing with the instant that x is 6 feet, so I'll write a 6. We know that dx over dt is 4 feet per second, so let's write a 4 plus 2 times y, which we discovered was root 864. Root 864 times dy over dt equals 0. And from here, now we have what we need to solve for dy dt. So let's do that. We know that 2 times 6 times 4 is 12 times 4, which is 48. 48 plus 2 root 864 times dy over dt equals 0. Subtract 48 from both sides. 2 root 864 dy over dt equals negative 48. Let's move this down a bit. Divide both sides by 2 root 864. It's going to be dy over dt equals negative 48 over 2 root 864. And we know that the units that we're dealing with, as it was set up here, is feet per second. So let's just write feet per second next to our answer. Feet per second. And there is our solution. So what we found is dy over dt. Okay, so when the base of the ladder is 6 feet away from the wall, how fast is the top of the ladder sliding down the wall? So we found the rate at which this distance y is changing, dy over dt. Another thing to note is we notice that this value is actually negative, right? And this makes sense because if we take a closer look at our drawing, I'll write this in white. We know that this x value right here is moving to the right. So I'll draw just an arrow to the right here. And we know that this y value, this top of the ladder, is going to be sliding down. So I'll draw a down arrow. And since we know that this is the positive y direction, it only makes sense that y is going to be, the rate of change of y is going to be negative since it's going down. So one more thing to note is that it is okay to leave our answer just like this. We do not need to simplify on an AP test. If your teacher would like you to simplify, then please do. But the AP graders will not care if you leave your related rates answer just like this, at least on the FRQ portion. In my opinion, it is not smart to try and simplify. One, it takes up time, and 2, it makes room for error. So I think the smartest decision would just be to leave it like this. So let's move on to our second problem. So here we're given something very similar. This top portion is the same. A 30-foot long ladder is leaning against the wall. Its base is being pulled away from the wall at a rate of 4 feet per second. Then the second part is telling us that the wall, ladder, and ground form a triangle. And it asks us, what is the rate of change of the area when the base of the ladder is 8 feet away from the wall? So let's apply these same 4 steps that we did last time. So what we'll do is we'll make a drawing. So let's just draw a wall like so. We'll draw a ground. Then we'll draw a ladder. So just like last time, let's label our values. A 30-foot long ladder, so we know that this value is going to be 30 feet. And again, since it's an object, this value is going to remain constant. It's never going to change. Then we have the base is being pulled away from the wall at a rate of 4 feet per second. So that is referring to this distance right here. So we'll label this distance x. And it tells us that the rate at which x changes is going to be 4 feet per second, just like last time. So dx over dt is going to be 4 feet per second. And this time, it tells us that the wall, ladder, and ground form a triangle. The triangle is right here. And what is the rate of change of the area? So we know that we're dealing with the area. We'll write that here. When the base of the ladder is 8 feet away from the wall. So this time, we're dealing with the instant that this x value is going to be 8. So let's label that here, x, the instant that x is 8 feet. And so here are all of our values that we are given. So this time, one thing that I noticed is that we're dealing with this a right here. We're dealing with the area of a triangle. And to foreshadow a little bit, we know that the area of a triangle is going to be, the equation is going to be 1/2 base times height. So we have a base right here, which is x. We're dealing with the instant that x is 8. But we need the height in order to solve this. So again, let's use the Pythagorean theorem to solve for this unknown value. And just like last time, let's call this value y. So a squared plus b squared equals c squared. Then we plug in our values. A squared is 8 squared. 8 squared plus our unknown. So y squared equals the hypotenuse squared, which is 30 squared. So that, if we solve that, it becomes 8 squared, which is 64, plus y squared equals 900. Y squared equals 836, and we get that our y value is going to be 800, the square root of 836. So let's write that here. So what this tells us is that at the instant that this distance is 8 feet, this distance is going to be root 836 feet. So here we've set the foundation for all of our values, and our next step, again, is to find the formula. So like I mentioned before, the equation that we're going to be dealing with is the area of a triangle, and we know that that is just a, or area, equals 1/2 base times height. So there we have our equation, and let's just rewrite that so that we're using these values that we have, or these variables, excuse me. So a equals 1/2 x times y. So the problem is asking us to find the rate at which the area changes. So in order to do that, we need to implicitly we need to differentiate with respect to time in order to find the rate of change with respect to time. So let's do that in pink. So dA over dt equals, and we have x being multiplied with y, so we're going to be using the product rule here. So let's draw a 1/2 with a square brace. We'll label u as x and v as y. U prime times v, so u prime is just going to be 1, or excuse me, dx over dt times v, which is just y, plus v prime, which is dy over dt, times u, which is just x. And let me just distribute this out. dA over dt equals 1/2 dx over dt times y plus 1/2 dx over, or sorry, dy over dt x. So here is the equation that we are working with. Now, from here, all we need to do is just plug in all of our values. So I'll do that in blue. dA over dt is equal to 1/2. And we know that dx over dt is going to be 4 feet per second. So I'll write a 4. We know that y is going to be root 836. So root 836 plus 1/2. We know that from last time, dy over dt is just going to be, it's going to be negative 48 over 2 root 864. Let me move this over. And then our x value is going to be 4 feet. It's going to be 8 feet. So let's plug in that 8 feet. And from here, we have our equation, and now we just solve. So dA over dt is 1/2 times 4, which is 2 times root 836 plus 1/2 times 8 is 4 times 48 to root 864. And for this one, I'm just going to plug this into a calculator. If we do that, we get that dA over dt is going to equal 54.561. And if we take a look at our units, we know that we are dealing with feet per second. So the rate at which the area changes is going to be feet squared per second. So here is, and actually, yes. Here is the answer to our problem. So let's move on to our third example. In our third example, we're given the same first part. A 30-foot long ladder is leaning against a wall. Its base is being pulled away from the wall at a rate of 4 feet per second. So that looks the same. And then the next part tells us to find the rate at which the angle that the ladder and the ground make when the base of the ladder is 10 feet away from the wall. So let's apply our first step and draw a picture. So this is going to look very similar to what we had earlier. We have a wall, a ground, and a ladder that's leaning against the wall. So we know that the ladder is going to be 30 feet long. 30 feet long. So let's label that there. And this sentence tells us the base of the ladder is being pulled away from the wall at a rate of 4 feet per second. So that's referring to this distance. So that let's label this distance x. And the rate at which this x is changing, dx over dt, with respect to time, is going to be 4 feet per second. Equals 4 feet per second. So the second part tells us to find the rate at which the angle that the ladder and the ground make when the base of the ladder is 10 feet away from the wall. So this second part tells us that we're dealing with the instant that this distance right here is 10 feet. So let's write x equals 10 feet to tell us that this is the instant that we are dealing with. Then it's talking about the rate of the angle that the ladder and the ground make. So let's draw a little angle right there with a theta. And eventually we're going to be dealing with d theta with respect to time because we know that we're dealing with a rate. So for now, let's just leave this picture as is. In the future, we are going to have to come up with some more information, but let's just see, let's just find the formula and differentiate in order to find what more we need. So if we go down a little bit, let's find the formula that we're going to be using in green. And if we take a look at our drawing here, we know that we're dealing with some side lengths, and an angle. And we know that the equation that provides us with the relationship between the side lengths and the angle are going to be trig functions. So here, if we're going off of this angle, we know that we have the adjacent side and the hypotenuse side. So our relationship is going to be cosine. So cosine of theta is going to equal, and our adjacent side is just going to be x over 30. And notice how I plugged in the 30 right now, because this 30 is never going to change. This is an object. Whatever we do to it, the length of it is not going to change. Whereas this x, we're dealing with this 10 feet, but this is only an instant that we're dealing with. So right now, for the overall solution to our problem, we should just leave this x as is. So from here, I'm just going to rewrite this as cosine theta equals 1 over 30x, just so that it's easier to differentiate. And let's actually do that now. Let's find the derivative with respect to time. So the derivative of cosine is going to be negative sine and negative sine theta. And we know that when we differentiate with respect to time, we have to write a d theta over dt next to it. And then this is going to equal 1 over 30 times dx over dt. So let's just quickly evaluate which values that we have right now. So we have this dx over dt value, but we do not have this negative sine theta value, right? We have this d theta over dt that we are trying to find, the rate at which this angle changes, but we do not have this sine value. So let's try to find the sine value, okay? So in order to do that, we have to take this angle and we take opposite over hypotenuse. But since we don't know our opposite side, we need to solve that using the Pythagorean theorem again. So I'm going to switch back to yellow and then write out the Pythagorean theorem. A squared plus b squared equals c squared. A squared, we're dealing with the instant that x equals 10, so I'm going to plug that in. 10 squared plus b squared, we'll call this unknown y. Y squared equals c squared, and that is referring to the hypotenuse, which is 30. Then from here, 10 squared is 100 plus y squared equals 900. Y squared equals 800. And we know that y is going to be the square root of 800. So let's write that here. Square root of 800. So now we have the information that we need to find what sine theta is. So I'm going to scroll down a little bit more just so that we have room to write. So sine theta is going to equal, sine is opposite over hypotenuse, so it's going to be root 800 root 800 over 30. So root 800 over 30. So there we have our sign relationship. So now, if we go back up here to our differentiated equation, we have all the values we need to solve. So now, let's plug in all of our values. So negative sine theta, which we discovered was root 800 over 30. So root 800 over 30 times d theta over dt, and we know that that's the value that we're trying to solve, equals 1 over 30 times dx over dt, which we determined was 4 feet per second. So let's write a 4 there. Then let's isolate this d theta over dt. So we have that d theta over dt. If we multiply both sides by its reciprocal, and then we make both sides negative, we get that d theta over dt is going to be negative 30 over root 800 times 1 over 30 times 4. And if we plug that into a calculator, this value is going to equal negative 0.141. And then our units, we know that we're dealing with the rate at which the angle changes, so that's going to be radians. And we know that our time is just going to be seconds. So our final answer for this problem is going to be this. So there is the third example. What we've just covered is 3 examples of ladder problems that we might see on the AP test. Now keep in mind that there will be other variations of the ladder problem, but these just cover the 3 types that you might see. Some advice that I have for you is that you need to come up with a good system of solving these so that you are comfortable with solving them whenever you see them. If you noticed in the first one, I took a more methodical approach in that I came up with all of the values first and then dealt with the equation, whereas in the last one, I took a little bit of a different approach and I listed the values and then came up with the equation that I used, and then I went back to solving more values that I ended up needing. So not only in related rates, but other math problems as well, it's good to build a sort of system for each kind of problem, and that way you can stay consistent in your studies and you'll have an easy time solving them. So I hope you enjoyed. If you have any questions, you can leave them in the comments, but that's it.